I want you to picture a scenario. You're working on a big project, maybe a presentation or, I don't know, a blog post. And you've got ChatGPT open in one tab to help with the writing, right?
Yeah, standard workflow these days.
Right. And then you've got Midjourney or Deli open in another tab to generate some visuals. And you are just stuck in this endless loop, copy pasting, downloading, re-uploading,
Oh, yeah.
trying to act as the translator between two completely different AI brains.
It's what we call tab fatigue.
Yeah.
I mean, you're basically trying to get the writer to talk to the artist, but they absolutely refuse to be in the same room.
Exactly. It feels super disjointed. You're just the middleman. But the research we are looking at today claims that this entire workflow might just be totally obsolete soon. So welcome to today's deep dive.
Thanks for having me.
Today, we're deep diving into a new paper from the team at FAIR that's Meta's fundamental AI research group, and it's all about a model called Chameleon.
And I just have to say right up front, this isn't just a feature upgrade. We're talking about a fundamental architectural shift. The researchers are calling this an early fusion mixed-modal model.
Early fusion.
Right, and the promise here is massive. They're talking about a single model that understands text and images natively at the exact same time without needing any kind of translator.
So effectively, the writer and the artist are finally inhabiting the same brain.
Precisely. No more switching tabs and no more switching contexts for you as a user.
Okay, but before we get into the how of it all, I really want to clarify why this is different from what we have right now. Because, I can already upload a photo to an AI and it can describe it to me. Or I can ask for an image and it generates one.
Yeah, it feels seamless.
Right. To the end user, that already feels like a mixed model. So what is Chameleon doing that's actually different?
That's the key question. So what you're describing, what most current models do, is what we call late fusion. Imagine you have a really smart text AI and you want it to see. You basically glue a pair of glasses onto it. You use a separate vision encoder that looks at an image, translates that image into a text description or a mathematical summary, and then feeds that summary to the language model.
Oh, I get it. So the language model never actually sees the raw pixels. It just reads a report about the pixels.
Exactly. It's like, okay, it's like if I described a sunset to you, you can write a beautiful poem about it based on my description, but you didn't experience the sunset yourself.
Right. I'm just taking your word for it.
You're relying on my translation. That's late fusion. It works, but it's inherently disjointed. The text side is always going to be the bottleneck.
And Chameleon is early fusion.
Right. With early fusion, there is no separate vision encoder. There is no translator. The model is trained from scratch to process raw images and raw text as the exact same type of information. It learns to see and read simultaneously.
That sounds great conceptually, but I'm trying to wrap my head around the mechanics of that. I mean, text is words, syntax, grammar. Images are pixels, colors, shapes. How do you feed those two completely different data types into one neural network without it just turning into garbage?
It all comes down to tokenization. You know how large language models break words down into tokens?
Sure, little chunks of text, like apple becomes a token, ing becomes a token.
Chameleon does the exact same thing for images. It literally takes a 512 by 512 image and chops it up into 1024 discrete tokens. It flattens the visual information into a sequence.
Wait, pause there. 124 tokens for a whole image. That seems, I don't know, really low.
It's surprisingly efficient. To the model, that sequence of image tokens looks just like a sentence. It's just a really long, weird sentence. So when you feed it a document that has text and pictures, it doesn't see a text block and an image file. It just sees a continuous stream of integers. Some represent words, some represent patches of an image.
So to Chameleon, a photo of a cat isn't a visual object. It's just a paragraph of cat-shaped code.
In a sense, yeah. And because of that, the exact same transformer architecture, the same mathematical engine, processes the text questions and the image answers indiscriminately. It projects everything into a shared representational space from inception.
That feels like it would solve that lost in translation issue we talked about earlier. If the model is looking at the raw tokens of the image, it's not relying on your summary of the sunset.
Exactly. It sees the sunset. And that brings us to the real breakthrough capability here. They call it interleave generation.
Which means what, in plain English?
It means the conversation can flow back and forth between modalities in absolutely any order. Most models today are rigid. It goes input image, output text, or input text, output image.
Right.
But Chameleon can go text, then image, then text, then image. It weaves them together naturally.
The paper had that banana bread example. I thought that illustrated this really well.
Oh yeah, it's a classic use case. So
Okay.
a user uploads a picture of a bowl of overripe bananas and asks, what can I bake with this?
Standard stuff so far.
Right. Chameleon looks at the image tokens, recognizes the bananas natively, and starts generating text tokens for a recipe. It writes the ingredients, the instructions, and then right in the middle of the response, it switches modes.
Without breaking a sweat.
Exactly. It generates image tokens to show you what the baked loaf should look like right there in the flow.
And it does this without calling an external tool.
Correct. It doesn't stop and say, hey, calling doll. It speaks in pictures for a moment,
Yeah.
then goes right back to speaking in words to finish the advice.
That flows much more like a human explanation. If I were teaching you to bake, I'd talk, show you a picture, talk some more. I wouldn't send you to a different room to look at a sketch.
Exactly.
Yes.
It's fluid.
But there was another example that caught my eye because it felt like a logic trap. The stop sign test.
Oh, this was fascinating. This really tests the reasoning part of the brain.
So if you're listening, they show the model a picture of a stop sign in a forest. And they ask it to do 3 things. Find the best hiding spot for a chameleon, generate a camouflage pattern for that spot, and then this is the kicker, rate its own success.
Multi-step reasoning across modalities.
Mm.
First, it has to analyze the scene. It correctly identifies the red stop sign as the hardest place to hide because it contrasts so sharply with the green forest.
Which implies it actually understands color relationships and context.
Then it generates an image of a chameleon with this mottled brown and red pattern to try and blend into the sign.
And then comes the self-critique. The model rates its own drawing a 2 out of 10.
It was brutal on itself. It explained that the red on the stop sign was too solid and bright, and its own camouflage pattern was too messy to actually blend in.
Okay, but this is where I get stuck. If the model is smart enough to know it's a 2 out of 10, why didn't it just make a better drawing? It's the one holding the pencil.
That's a great question, and it really touches on how these autoregressive models work. When it's generating the image tokens, it's doing it one by one, predicting the next piece of the puzzle. It's purely in creation mode.
Okay.
Once the image is done, it switches back to text mode and looks at what it just created.
So it creates blindly, in a way, and then looks at the result with its critical eye.
Exactly. The critic part of the brain is analyzing the output of the artist part of the brain, even though they are literally the exact same brain. It shows a level of introspection we don't usually see. It didn't just hallucinate that it did a great job. It grounded its critique in the visual reality of what it actually produced.
That honesty is refreshing, even if the drawing sucked. Huh. But another thing they showed was that bird-watching request. Someone asks for cool, quirky-looking birds. And the model describes a toucan, drops in a generated image of one, then moves on to describe a puffin, drops in an image of that. It just flows like a textbook or a blog post.
It's a complete paradigm shift for document generation.
But listening to this, it sounds effortless. Just treat images like text. Problem solved. But if it were that easy, OpenAI or Google would have done this years ago. The paper makes it clear that building this was actually an engineering nightmare.
Nightmare is probably the right word. The researchers describe it as a massive engineering struggle. When you try to train a single model on these 2 very different types of data simultaneously, you run into a huge problem called divergence.
Divergence, which means the training crashes.
It means the model stops learning entirely, or the math just spirals out of control. The root cause is super interesting. It's all about competition between the modalities.
Competition, like the text and the images are actually fighting each other.
In a mathematical sense, yes. Think about it. Text is discrete, symbolic, highly structured. Images are continuous, noisy, dense. They have completely different levels of entropy or randomness and complexity.
Right.
When you throw them into the exact same neural network, they start competing to increase their norms, basically the volume of their signals.
Okay, it's like having a heavy metal drummer and a whisper-quiet acoustic guitarist trying to record on the exact same microphone. The drums are just going to blow out the audio.
That is a perfect analogy. The image signal is the heavy metal drummer. It's so dense and loud that it completely overwhelms the text signal. The model focuses all its attention on the images and starts ignoring the text. Or the gradients just explode because values get too high.
So how do you mix the tracks so you can actually hear both?
They had to introduce a new mechanism called QK norm, or query key normalization.
Okay, jargon alert. What is QK norm actually doing under the hood?
So in a transformer architecture, the attention mechanism is how the model decides what to focus on. It compares a query, what I'm looking for, with a key, what I'm looking at. QK norm basically applies layer normalization directly to those vectors.
So it literally is a volume knob.
Essentially, yes. It forces the loudness of the signals to stay within a very specific range. It prevents the image norms from spiraling up and drowning out the text. It enforces a truce so both modalities can be learned at the same time.
But that wasn't enough for the big model, right? The 34 billion parameter version.
No, the big model was even more unstable. For the 7 billion parameter model, they used some dropout techniques. But for the 34B one, they had to go a step further and use something called Z-loss regularization.
Yeah, I saw that in the paper. It sounded like something out of a theoretical physics textbook, penalizing the partition function.
It sounds intimidating, but let's simplify it. At the very end of the neural network, there's a function called softmax. Its job is to turn all the raw numbers into probabilities, basically deciding which token comes next. To do that, it has to sum up all the possible options. That sum is a partition function.
Okay, I'm with you. It's the sum of all possibilities.
Right. Now, during training, those raw numbers can start to drift upward, getting bigger and bigger. Imagine a helium balloon that just keeps expanding and floating higher. If it gets too high, the math stops working efficiently. The model gets confused.
So the balloon floats away into infinity and the model crashes.
Exactly. Z-loss is like a gravity tether. It adds a penalty to the equation that pulls that sum back down to zero. It forces the balloon to stay close to the ground. It keeps the internal math grounded so the model remains stable over weeks and weeks of training.
It's fascinating that we have to invent entirely new math just to keep the machine from confusing itself when it looks at a picture.
It really is.
So they fixed the stability, they got the drummer and the guitarist to play nice. The big question is, was it worth it? Does Chameleon actually perform better than the glued-together models we've been using?
It does, and the results are actually somewhat counterintuitive.
How so?
Well, you'd expect it to be good at image tasks. And it is. Chameleon 34B achieves state-of-the-art in image captioning and visual question answering. It completely beats models like Flamingo ADB, which is more than twice its size.
Wow, so efficiency wins.
But the real surprise was the text performance. Usually there's a trade-off. If you spend half your brain capacity learning to process images, you usually get dumber at text. It's the jack of all trades, master of none problem.
Right, you assume it would forget how to write good essays because it's too busy looking at JPEGs.
But that didn't happen here. Chameleon actually beats Llama 2 on text-only tasks, and it's competitive with Mixtral 8x7B.
Wait, it beats Llama 2, but Llama 2 is a dedicated text model.
Yes, and this suggests something really profound about intelligence. We used to assume that visual processing was a cost or a distraction for a language model, but Chameleon suggests that visual grounding might actually make the AI smarter at logic.
That makes sense, doesn't it? I mean, the real world operates on logic and physics. If you can actually see the world, you understand cause and effect way better than if you just read a textbook about it.
Exactly. Learning that a ball drops when you let go of it visually might reinforce the textual concept of gravity. By learning to see, it actually became a better thinker.
That is a huge takeaway. But benchmarks are one thing. What about how it actually feels to use? Because the paper mentioned they did a human eval.
They had to. This was necessary because there's literally no standard test out there for mixed-modal interleaved documents. It's too new. So they put Chameleon up against the heavyweights, Gemini Pro and GPT-4V.
But wait, GPT-4V doesn't do what Chameleon does. It can't generate images natively in the stream.
Right, so to make it a fair fight, they augmented GPT-4V, they hooked it up to DALL-E 3. So if the human prompt asks for an image like, brainstorm a logo for my truck, GPT-4V would call DALL-E, get the image, and paste it in. It was a simulation of the experience.
So it's the native brain versus the Frankenstein monster. Who won?
The humans preferred Chameleon. It won 60.4% of the time against Gemini Pro and 51.6% against the GPT-4V and DALL-E combo.
Why? Was the art just better?
Not necessarily the art quality itself, but the integration. Because Chameleon is one single brain, the images it generated were perfectly contextually aligned with the text it just wrote. With the Frankenstein approach, you often get disjointed results.
Like it doesn't quite match?
Right. The text says one thing, but the image shows something slightly different because the text prompt sent to DALL-E behind the scenes wasn't perfect.
It's the difference between drawing a sketch yourself to explain your own idea versus describing your idea to a sketch artist over the phone.
Precisely. The nuance is always lost in the handoff. But Chameleon has no handoff.
We should probably touch on safety briefly, because whenever we talk about generating images and text together, things can get really messy. If I ask it to write a hate speech manifesto and illustrate it, that's a massive problem.
Absolutely. The FAIR team did extensive red teaming for exactly this. They had experts throw thousands of unsafe prompts at it. We're talking controversial topics, violence, self-harm requests, but about 445 specific interactions in the study.
And how did it do?
It held up really well. Only about 1.6% of responses were considered unsafe. Because they fine-tuned it on safety data for both modalities natively, it learned to refuse bad visual requests just as well as bad text requests.
So, stepping back for a second, we have a model that completely breaks down the wall between seeing and reading. It proves that a unified architecture is not only possible, but potentially much smarter. Where does this leave us?
I think we're officially moving from the era of multimodal AI, which was really just different AIs glued together, to native mixed-modal AI.
Native being the key word there.
Yes. The success of early fusion really suggests that the future isn't specialized modules. It's a single, unified digital brain that processes all sensory data as one single language. It's a lot closer to how we function. I don't have a vision brain and a separate language brain. I just experience the world.
It effectively democratizes data. A pixel, a word, a piece of code, it's all just information to be processed.
And that actually leads to a really provocative thought.
Oh, what's that?
We've been talking about how Chameleon turns an image into 1,024 tokens, right?
Right.
Well, there's that old saying, picture's worth 1,000 words.
Huh. And in this case, it's literally 124 words.
It's mathematically accurate. But it makes you wonder, if the machine processes the image token exactly the same way it processes the text token, does the distinction between seeing and reading actually exist for the AI?
Wow. That's deep.
To us, they are totally different senses. To Chameleon, a sunset and a poem about a sunset are just two different dialects of the exact same language.
It suggests that maybe the barrier between senses is just a biological limitation, not a fundamental universal one. What a fascinating thought to wrap up on. We'll definitely be watching to see if early fusion becomes the new standard for all these models moving forward. Thanks for unpacking this with me.
My pleasure.
And thank you for listening to this deep dive. We'll catch you on the next one.